Good afternoon, my name is Patricia Johnson. The rate of decay of a radioactive source falls from 3,000 counts per minute to 2,000 counts per minute 5 minutes later. From this information, determine the half-life of the substance. Let's start with the equation for radioactive decay. A equals A naught times the exponential function raised to the power of kT. A is the quantity of substance remaining at any time t. A naught is the original quantity of substance. K is the rate constant for this particular substance, and T is the variable time. Let's write down what we know. We know that the rate of decay at time t equals 0 is minus 3,000 counts per minute, and the rate of decay at times t equals 5 minutes equals minus 2,000 counts per minute. Rate is the derivative with respect to time of the radioactive decay formula. The rate is negative because this is decay and not growth. By definition, at the half-life, 1/2 of the original quantity of substance is left. Let's summarize what we know in a table. We know specific values of rate of decay at points in time. We have our formula for the quantity of substance. We can calculate a formula for the rate of decay by taking the derivative with respect to time of this formula here. And we have our constant K. Let's try to determine an equation for the half-life by substituting into our radioactive decay equation. At the half-life, 1/2 of the original substance remains. We divide both sides by A naught to simplify the equation. We take the logarithm of both sides of our algebraic equation here to extract TH. And we make TH the subject of our algebraic equation to solve for TH in terms of K. Now we need a value of K in order to solve for a numeric value of TH. We do this by creating two simultaneous equations using the derivative with respect to time of our radioactive decay equation. We recall the rule for taking the derivative of an exponential to simplify this term. Now we have the rate equal to A naught times K times e to the KT. Let's summarize what we know in our table and update our table. So now we have rate at two specific times. We have a formula for rate of decay. And we can come up with our two simultaneous equations. At t equals 0, minus 3,000 equals A naught times K times 1. At t equals 5, minus 2,000 equals A naught times K times e to the 5K. Now we have our two simultaneous equations. We can solve for K in terms of A and substitute it into this equation here to arrive at a numerical value for A, which we do. A equals minus 3,000 over A naught. We substitute that into our equation up above, and we arrive at we take the logarithm of both sides to simplify our equation, and we use our graphics calculator to compute a numeric value for A naught. A naught equals 36,994.55. This is greater than 0, which makes sense because it's a quantity. Substitute A naught back into our equation where K was expressed in terms of A naught, and we get minus 3,000 over 36,944.55 equals minus 0.08109. This makes sense because our exponential function must have a negative power in the index in order for it to be a decay rate. When we substitute our value for K and A into our equation up above for TH, or actually we just have to substitute K, we express TH in terms of K, we get 8.5475 minutes. Is this correct? Is this reasonable? I don't really know. It looks good in terms that because it is greater than 0 and time is greater than 0. But let's substitute all our known values back into our rate of decay equation and see if we can calculate backwards and get to minus 3,000 counts per minute at t equals 0, which we do. Same for at t equals 5 minutes. We substitute our value for A and K, and we calculate minus 2,000 counts per minute, so that's correct as well. We can also validate our answer graphically. I like using Excel. I create a table of values here based on the timeline from 0 minutes up to 13 minutes, but it could go to infinity. And I compute the rate of decay at these points in times, and I also compute the quantity of A at these points in times. Then I graph the time on the x-axis, the rate of decay on the y-axis, and I check for reasonableness. At t equals 0, we have minus 3,000. At t equals 5, we have minus 2,000. And at t equals 8.5, which was our solution to the half-life, we have about minus 1,500 counts per minute. T 8.5 is about here. If this graph went out to infinity, it would never approach 0. So this seems reasonable to me. We can also check our answer in GeoGebra. Here I use 3 formulas. I plug in the formula for the rate of decay, where x here represents time, and this is graphed by the green line here. Then I simply plug in the constants, x equals 0 and x equals 5. So 0 minutes, 5 minutes. GeoGebra calculates vertical lines, which intersect our formula. Point A is at 5 minutes and minus 2,000 counts per minute, which makes sense. And point B is the intersection point at t equals 0, or in this case, x equals 0. And that gives us minus 3,000 counts per minute, and that makes sense as well. Thank you for listening.